So, in the previous example we saw a system where we had two distinct eigenvalues. Now, let us consider the second example. In this example we are given a system of differential equations with our matrix A equals to -2, 1, -4 and 3. As you can see, this is a 2 by 2 system, and we need to find two things. In part A, we want to find the general solution for this particular system. After we finding the general solution, we want to find the specific solution that satisfies this initial condition. IC stands for initial condition, and my initial condition says when, let's say, if my independent variable is time, then at time t equals 0, my solution x should be 1, 0. So, the first step is to find the eigenvalues of this matrix A. Now, as a good habit, always write this matrix A minus lambda I, because we are going to use this A minus lambda I matrix to calculate the eigenvectors. So, A minus lambda I should be, okay, subtract lambda from these diagonal elements, you will get -2 minus lambda, then 3 minus lambda. Now, your off diagonal elements stay as it is, so 1 and -4. So, this is your A minus lambda I matrix. Okay. To get the eigenvalues, what we need is the characteristic equation. So, the characteristic equation should be lambda squared minus, now minus, then this number should be come from the trace of this matrix. So, if you calculate the trace of this matrix A, it will be -2 plus 3, which is 1. So, you have negative times 1 lambda plus the determinant of this matrix, which equals to -2 times 3 is -6 minus -4, and this should be -2. Okay. And this one comes from the trace of this matrix A, and this number equals to the determinant of this matrix A. Okay. So, this is the trace A, and this is the determinant of A. Okay. So, now let us solve this second degree polynomial equation. In fact, we can factor this quadratic polynomial, and the factors are lambda minus 2 and lambda plus 1 equals 0. Okay. So, now we have two values for lambda. Lambda can be +2 or lambda can be -1. Now, as you can see, we have distinct or different eigenvalues. One eigenvalue is 2 and the second eigenvalue is 1. The next step is to calculate the eigenvectors for this eigenvalue and for this one. So, let us pick the first, let's pick the first eigenvalue lambda equals to 2, and now to find the corresponding eigenvector we should solve this equation. Okay. Now, A minus lambda I, this equals to, so basically we want to evaluate this matrix at lambda equals 2. If we do that, so we have -2 minus 2, which is -4, 1, -4, and then since lambda equals to 2, we have 3 minus 2, which is 1. This is your A minus lambda I matrix times vector V. Our eigenvector V should have two components. So, let us say they are A1 and A2 equals to 0, 0. Now, as you can see, your first equation is negative 4A1 plus A2 equals to 0, and in fact your second equation is exactly equal to this one, because you will get negative 4 times A1 plus A2. Okay. So, I am going to solve for A2, and if you solve for A2, you will get A2 equals to 4A1. Add plus 4A1 to both sides, you will get A2 equals to 4A1. So, now as you can see, we have one equation with two variables. So, we have infinite many solutions. So, let us pick A1 equals to 1. If A1 equals to 1, then A2 should be 4. Therefore, the corresponding eigenvector, let's say the corresponding eigenvector V equals to, first component is 1, the second component is 4. Great. So, now we calculated the eigenvector that corresponds to this eigenvalue. So, now let us find the eigenvector that corresponds to lambda equals to negative 1. If lambda equals to negative 1, so this is lambda 2, just lambda 2 equals negative 1. Again we need to solve the same system, A minus lambda I times vector V equals to 0. Since lambda 2 equals to negative 1, the value of A minus lambda I matrix should be negative 2 minus minus 1, 1, negative 4, 3 minus negative 1 times, let us say A1 A2 equals to 0, 0. Okay, now let us simplify this. So, we have negative 2 minus negative 1, so this is plus 1, negative 2 plus 1 is negative 1. So, we have 3 minus minus 1, which is positive 4, 1, 2 equals to 0, 0. Okay, let us simplify this system. If you multiply this matrix and our vector V, you will get negative A1 plus A2 equals to 0, and negative 4A1 plus 4A2 equals to 0. As you can see, if you multiply this first equation by 4, you will get this second equation. Okay. So, I am going to consider first equation because it is more simpler than the second one, and from this we get A1 equals to A2. So, if we set A1 equals to 1, then our A2 equals to 1. With this, we can get the second eigenvector V2 that corresponds to lambda equals to negative 1. Okay. So, we have found the eigenvalues and eigenvectors for this matrix A. So, next step is to get the general solution, and to get the general solutions we need to consider a linear combination of the solution that comes from these two eigenvalues.